All right, so in this video, we're going to derive the S4 character table. This isn't a very common point group, although there are several molecules that fall into this class. Definitely hard to come up with these, a priori, but here is an example of a molecule. This is a tetrabromoneopentane, so it's an organic molecule. There's some inorganic complexes as well that also have this point group. But basically, as the name implies, the principal rotation axis is actually an improper rotation axis, and that's an S4. And so you can see that right here. And remember what an S4 is an S4 is, we use the hat notation here to show that we're doing an operation and not a class. It's a C4 followed by a sigma H. So that's a 90-degree rotation followed by perpendicular horizontal mirror plane, which is perpendicular to that C4, so that 90 degrees. So what you're going to do here is you're going to do 90 degrees along this axis, this S4 axis, and then you're going to do a mirror plane flip down to the other side. So this bromine, for example, if we rotate it 90 degrees, it's going to end up over here. We're going to do that rotation, and then we're going to flip it down into that bromine. So that's how there's symmetry. See, similarly, you can see for this hydrogen, we would flip it to where this bromine is, but then it goes down. We rotate it to where this bromine is 90 degrees, and then we flip it down below the mirror plane where the hydrogen is. So that's how this symmetry works. So that is an S4. And that's really, other than identity, and of course we always have identity, that's the only symmetry operation fundamentally that we have. And then we have symmetry operations that are derivatives of doing the S4 or consequences of doing the S4 multiple times. So if you look at what happens if I do the S4 twice, well, this would be a C4 twice followed by a sigma H twice. Well, C4 twice, that's a 90 degrees twice. That's just the same as a C2. And then if you do a sigma H twice, that's the same as doing nothing as identity. Because if we flip from top to bottom, and then do another sigma H that I take from bottom to top, you just do nothing, you stay in the same point. So an S-force twice is the same as C2. So we should have a C2 operation in this molecule, which is 180-degree rotation. And indeed we do, you can see it here. So it's in the same axis, coincident with S4. And see it takes this bromine, spins it over there. It takes this bromine, spins it back to that bromine. Okay, it's 180 degrees. And then we can see about doing an S4 three times. That would be doing a C4 three times, followed by a sigma H three times. If you do that, sigma H three times is the same as doing just one sigma H, right? Because you go from top to bottom, for example, bottom to top, and then top to bottom. Well, that's the same as just doing top to bottom. So C4 three times, S4 three times is C4 three times, 270-degree rotation, followed by a sigma H. If you do an S4 four times, you're going to get yourself back to identity because you have sigma H four times, and that's an even number of flips, top to bottom, bottom to top, top to bottom, bottom to top. So you end up just doing top to top, it did nothing. And C4 four times is a 360-degree rotation, that did nothing. So S4 four times isn't unique, you're back to identity. And it turns out that these four symmetry operations, the E sigma, the S4, those are the only symmetry operations in the S4 point group. And these symmetry operations are all in their own class. In a lot of my other character table derivation videos, we've talked about whether or not, how do we know whether or not to put operations in the same class? And in some of those videos, some of those point groups, we have things like S4 and S4 three times in the same class. But we have to have some other symmetry operation. Usually this is a mirror plane, okay, or a perpendicular C2, which we don't have either of those in this class, that interconverts Cartesian coordinate systems, axis systems, that would make these equivalent. Because at face value, these sort of look equivalent, right? One is 270 degrees followed by flip, right? The S4 3 times. The other is 90 degrees followed by flip. And if you define your axis systems in the opposite way, those would be the same or equivalent. But we can't interconvert those axis systems with some other symmetry operation like a sigma D or sigma V are common ones that would do this. And we don't have those operations in this class, in this point group. So for those reasons, these four symmetry operations belong in separate classes. So once we know that, then we can start to actually derive the irreducible representations of our character table. So at the top of the character table, we put our different classes. And again, each operation in this case is in a unique class. So I have E, I have S4, we have the C2, the S4 twice, and the S4 3. And I dropped the hat notation because now we're talking technically about classes, although in this case, operations and classes are the same because there's only one operation in each class. And so our first character table rule tells us that we have an equal number of irreducible representations as we do classes. So we have 4 classes, so that means we're going to have 4 irreducible representations. Okay? And so we're, for now, just going to call these gamma 1, gamma 2, gamma 3, gamma 4. Later on at the end, we'll assign Mulliken symbols, which are the labels that give us some information. This is just how chemists talk about the different irreducible representations or vectors in the character table. Just a handy way of talking about them. But for now, we just give them these generic terms because we don't know what the irreducible representations are, so we don't know how to name them yet with the Mulliken symbols. But the first thing we always do is we plug in the, put in the totally symmetric irreducible representation, ones across the board. That's sort of a freebie that we always get. And then at this point, we start testing different functions. So function that I always like testing, start with the linear function, start with Z. And so we're going to ask the question, how does the Z-vector transform with these different one symmetry operation in each class? And so we can visualize the Z-vector as this red arrow pointing up along the Z-axis. And then we ask the question, hey, if I do the identity operation, what happens to the Z-vector? Well, you get back Z. And the one-by-one matrix that mathematically describes this transformation is just a one-by-one matrix with the element 1. We then take the character or the trace of this matrix. It's a one-by-one matrix. That's the sum of the characters along the main diagonal. We use the Greek letter chi, and we say the character or chi of E is just equal to 1. And so right here under gamma 2, we have a value of 1. We're hoping that when we go through this, we don't get ones across the board, positive ones across the board again, such that we can derive, a new irreducible representation. What happens if we do S4? If we do an S4, well, first, an S4, remember, is a C4 followed by a sigma H. When we do a C4, we're doing a 90-degree rotation on that Z vector. So when we do a 90-degree rotation like that, because this 90-degree rotation is wrapping around the Z-axis, that's not changing anything to the direction that this arrow is pointing, which is up. So that C4 does nothing. However, when we do a sigma H, remember sigma H is perpendicular to our principal rotation axis. Now, so it's going to be in the XY plane. Now that red arrow, that Z vector, is on top of that plane, so it's going to see itself in the bottom of the plane, and that mirror plane, therefore, is taking Z to negative Z. So the C4 component did nothing. The sigma H component took Z to negative Z. So overall, we have Z going to negative Z, and we have a one-by-one matrix with the value of -1 that describes this transformation. We take the sum across the diagonals, well, there's only one element in it, and so chi, or the character of C4 operation on Z, is -1. And so that means we put -1 as our character there. Next, we do C2. C2 is going to take Z to Z. And the same reason as we talked about before, now it's a 180-degree rotation, but still that Z vector is going to be pointing up. So we have a 1-by-1 matrix, and we take the trace of that matrix, and that gets us just 1. So we have a character of 1 here. Last one is the S4 3 times. And if you remember that, that's a C4 3 times. We figured out on the previous slide, followed by sigma h. And what is that going to do? Well, 270-degree rotation does nothing to the direction of Z vector, but we do have this 1 sigma h that takes Z to -Z. So I think you can see by now that you're going to get a value of -1 when we take the trace of that matrix. Okay, so this allowed us to derive another irreducible representation. Next vector I like to test is x. So let's do the same sort of thing. And here when we do identity on x, again, we get x going to x. When we do an S4 on x, what happens? Well, let's draw out our x vector. When we do a 90-degree rotation, right, we have to do a C4, then a sigma h. That is going to spin our x vector into y. And so what this immediately tells us is that x and y transform together. So we rewrite it like this. We can't describe x without describing y, and actually vice versa. Because if we look at the y vector, now let's draw a y vector in like blue, that's going to spin 90 degrees into -x. So y is going to go to -x. And then we're going to have a sigma h, and it's right followed by that, right? Because remember, this is just doing a C4. But remember, we do a sigma h followed by that for S4, but the sigma h is in the xy plane. So the x and y vectors are in that mirror plane, so they don't do anything. They're not above or below it. So that part doesn't do anything. So net, we just do this C4 effect. And it's telling us that because x and y transform together, we have to keep these x and y functions together in a 2-by-2 matrix. And that 2-by-2 matrix has zeros on the diagonal, and off-diagonal elements are 1s and -1s. That is matrix multiplication way of showing how x goes to y and y goes to -x. And when we take the trace of this matrix, we get chi of S4 operation equals 0 plus 0, okay, which equals 0. So under S4, we got 0. And for identity now, we have to say, well, we know we have to keep x and y together. So now we have the identity matrix that explains how x and y go to x and y. That's 1s across the main diagonal. We take the trace of that matrix, and we get 1 plus 1, which is equal to 2. So we got a 2 here. For the C2 operation, we're going to get x going to -x and y going to -y. Why is that? Because we're spinning the x-axis around completely to negative itself and the y-axis around completely to negative self. 180-degree rotation, right? So that matrix is -1s across the diagonal. And so that takes x into -x and y into -y. We take the trace of that matrix across the main diagonal, sum across the main diagonal, and we get -1 plus -1, which is equal to -2. Our last one here is S4 3 times operation. We know that's a C4 3, followed by sigma h. We already discussed about how the C4 3 doesn't do anything. And so if we think about what a 270-degree rotation does, the C4 3, to the x vector, it's going to spin it all the way around to negative y. Now the y vector is going to spin around to x. But the effect of this is, again, you're going to have, just like for S4 operation, you're going to have only 1s or -1s on the off diagonals. You're going to have 0 on the main diagonal when you do the matrix multiplication. So that is the matrix that explains this transformation. We take the sum across the main diagonal, you get that the chi for the S4 3 operation is equal to 0 plus 0, which is equal to 0. Now, that is looking fine. And if we look at things like orthogonality here of gamma 3 with gamma 1 and gamma 2, they are orthogonal. Problem is that we have another rule of the character table, which we kind of overlooked, which is that the sum of the squares of the dimensionalities, that is the character underneath the identity operation, has to equal the order of the point group, which is the total number of symmetry operations in the point group. Total number of symmetry operations is 4, right? We have one operation in each class. Sum of the squares underneath the identity operation gives us 1 plus 1 squared plus 1 squared plus 2 squared, just taking the sum here. And that equals, doesn't equal 4, okay? So we have a problem here. We've violated our character table rules. What that tells us is that we have actually a character where we have to use complex or imaginary numbers. And so this gamma 3 is actually going to split up into two components. And each of these, the dimensionality here is going to be 1. And we're going to have other characters here that some of these could be are going to be imaginary. And this is where sort of the math gets funky, but for everything to be orthogonal, work out, that's what we have to do. And so I'll show you how to do that in part 2 of this video.